Welcome to Real Physics. This is a talk given at a beautiful conference in Munich on physical and mathematical ontology. Many thanks to Chris from Dirac, the physics channel, for organizing this fantastic event. And well, I'm talking about the incompleteness of gravity, but basically about everything what's interesting in physics from my view. So I hope you enjoy this talk. Welcome to this conference and to my talk. I'm so glad that not everybody is coming to Munich for the beer. Even if I think the heyday of physics in Munich took place 100 years ago. So, well, where we start, I talk about the incompleteness of gravitational physics, and what we hear usually is preposterous claims like, we know what happened 10 to the minus 35 seconds after the Big Bang, or things like that. Let's say that, well, science has never been enthusiastic, bold talking, but asking questions. So I'm not going to focus on how much nonsense I think this is. But on the other hand, we have also serious science that claims to be something like precision cosmology or things like that, and clear picture of the Big Bang and everything, how that happened. And then there are people saying that with respect to gravitational physics, it's tested so well, 99%, that's proves Einstein at least 99.99%, right? Well, okay, but you can't just count the evidence in favor, but you have to look also at the contradicting evidence. And yeah, seriously contradicting evidence is something like the rotation curves of galaxies. And what we're observing here is flat rotation curves, more or less gas and the outer stars rotating with the same velocity, while it is expected at the same time from Newton's and Kepler's law that the velocities should decay in the outer regions. And there's no shred of doubt about this evidence. Hundreds or thousands of galaxies show this behavior. And the problem is that this is very well described by MOND, modified Newtonian dynamics, it's called. And by the way, I'm not a proponent of MOND. I have nothing to do with it. I think it's theoretically unsatisfactory. But you don't have to believe in MOND, but you have to acknowledge that MOND contains that heavy poison of that acceleration more or less equal to c over the age of the universe. And that's terrible, because even if you don't believe in MOND, the only reasonable conclusion is that either all these spiral galaxies agreed upon fooling today's astronomers, or general relativity, and by inclusion also Newton's gravity, is in a subtle but fundamental manner wrong. And the reason why the first hypothesis is preferred, because the alternative is so scary to contemplate. That's, I think we shouldn't forget about that. Not engage too much in discussions what's wrong, what's right, but this is proof that something seriously is wrong with the conventional picture. And if we switch not to dark matter, but to dark energy, let's talk about the expansion of the universe. I hope you can read this. It's a little bit written, but I have taken this slide from a talk by Martin Lopez Corredera, who's an excellent astronomer reviewing the evidence and the contradicting evidence also for the standard model. And you have so much evidence that is in blatant contradiction with the Lambda CDM model, such as metallicities, such as dust. I'm not going into detail this. I encourage you to read the papers. Cold gas, quasars are not in alignment, and then you have the Tolman test, and you cannot explain all this structure formation in the universe. And most importantly, maybe there is a contradiction with the size of the galaxies. even the latest measurements of the James Webb Telescope indicate or show that the galaxies are much too small. They should be on this line here, according to the Lambda CDM model, and they're just far off. I mean, what else do you need as a disproof of the standard model than such a huge deviation? So I think, yeah, the standard model of cosmology is either disproved or just a mess of parameters. But well, if you like to believe it and if you want to massage these parameters, so good luck with that. Yeah, another interesting piece of evidence against it was recently pointed out in this video, referring to a paper by Pavel Kurpa. And I mean, the standard model is going to solve this. I should go back. Is probably going to solve that by introducing now dark substance or dark physics or dark observations or whatever dark, you know. But somehow you're going to fix it. But it's nice to see that what happened to the last fix was, okay, if we have full-fledged galaxies at, say, at redshift 10 or 13, so what happened? Oh, we need this process of galaxy formation to speed up a little bit. So the problem is, if you speed up that process of galaxy formation, you got very bright stars in a short period that should be visible in the cosmic microwave background as a relic and significantly contribute to this and spoil the evidence that created the problem in the first place. So somehow, in a funny way, the dog bites into its own tail here. And yeah, that's just another piece of evidence that something is wrong here. And I think it's clear that we have to bid goodbye to that idealized picture of how science should work: general principle, induction, deduction, observations, revision, prediction, concepts, and so on. And real science is more like this. We start out from a beautiful theory, and then we make precision tests. Something is wrong here, anomalies. Okay, we got it digested, getting used to, add a free parameter. It's just a little bit less beautiful, the theory, and then the cycle goes on. But yeah, after 10 iterations, you should get out and, yeah, why the hell is nature like that? I mean, why do we need this increasing number of parameters? And yeah, I should add that you believe sometimes particle physics is laboratory clean, it's better off, but it's even worse there. But we're talking about cosmology today. So yeah, what I would like to say here, okay, most of you would probably agree here. But as I said, you did not come, was not the first motivation, but some of you came actually for the beer. I noticed yesterday. I was the one with sparkling water, but everyone else ordered the beer here in Munich. And I hope you didn't do that today, because if you take a sober look at the facts, the problem is even much bigger than this mess of the standard model, because I think very significant fundamental questions are swept under the rug. And I'd like to take the perspective of my favorite philosopher, if you allow me, Ludwig Wittgenstein. Don't get involved in partial problems, but always take flight to where there is a free view over the whole single great problem, even if that view is not yet clear. And I really like that. And there's also a funny anecdote about Heisenberg and Dirac having different approaches how to tackle a physical problem. And they compare it how to climb a mountain. And basically, it's Dirac saying that, well, you have to do one step after another. And then you have climbed a certain plateau and then look around and what's the next possibilities and just keep going and keep working. And Heisenberg instead said, no, you ought to take a look at the entire mountain and see where possible ways can go up. And then at the end, you may have to work out the details. And as a method, I very much side with Heisenberg here, even if I don't like, I mean, I prefer much more Dirac's concrete proposals of seeing the unified picture, whereas in my view, Heisenberg was too focused and too, well, too seeking too much agreement. Yeah, he was the one coming back from the 1927 Solvay conference claiming that everyone almost agreed, so I won here. No, that's not the way science works. So I want to take this kind of broader view, open up even a little bit the topic of gravity, and then again narrow down and see, not lose sight of the big problems here. And how are we going to do that? Well, we keep in mind a few important principles of good science, of course, falsifiability and empirical tests, and that's clear, but maybe it's not the whole story. We should also remind principles like simplicity among different theories, choose the one which is simpler, and I will extend this a little bit later. So William Occam is a very important figure, I think, here, and he fought the Pope and was in Munich. So hopefully we have more than one thing in common with him. And well, how to synthesize this? I'm grateful you mentioned also Arthur Schopenhauer, and he said the question of why is the foundational form of all science. And I would like to focus on the idea of explanatory power. And well, take just the gut feeling. Maybe it's not well defined or not easy to define, but I mean, we as theoretical physicists want to find real explanations for phenomena, not just grabbing another parameter and describing it or come up with some fancy mechanism because we do like it, because it has to be a logical, cogent reason for everything. And my personal take is that we should focus more on fundamental constants. Fundamental constants are, in my view, really the key to the deep problems of physics. And well, Einstein's, I agree completely here, numbers arbitrarily chosen by God do not exist, and their alleged existence relies on our incomplete understanding. I don't think this message has sunk into the scientific community properly until today. Also the other one, by the way, a very nice book by Ilse Rosenthal-Schneider. And I cannot imagine a theory containing an arbitrary number which could have been chosen by the creator just in another way. And yet, I mean, conventional physics is dealing with all these numbers, and some of them are obviously, okay, ad hoc postulates and an exercise in parameter fitting, but there are also more fundamental numbers we should explain. Like, I come back to the gravitational constant, it's also a number we should put into doubt, or at least try to explain. So my approach to how to tackle fundamental physics is a three-step process of how scientific revolutions occur. I think there is always a visionary idea, a mathematical formalism, and then you end up with the elimination of a constants of nature, which is a simplification. And that's why that's the hard way I would define what do you mean by simple in the sense of Occam's razor. And simplification means that you just get rid of free parameters. You express one thing by other constants of nature, you have an equation, and then you have a revolution. I pointed that out in my book, in a paper here in Physics Essay, Constants of Nature, Simplicity, Revolutions and Simplicity. And it's also outlined in my book, The Mathematical Reality. Let's say 2/3 of it is this theory of how to get rid of constants and constants of nature. And well, but maybe, today I shall focus on the unification aspect also of this. Regularly, if you find such an equation, it contains also a unification of different parts of physics which were not linked before, but maybe I should become more concrete. And what sparked the idea was, I mean, you look at maybe the most consequential scientific revolution light is an electromagnetic wave. Wow, okay? That you have, of course, a lot of people contributing, Kirchhoff and Weber, originally around 1857 or something, thinking about this epsilon dot mu naught could be equivalent to 1 over c squared. And that was the idea. But of course, you need also an entire theory or ontology, or how you want to call it, of Maxwell's equations to justify that. No doubt about that. But at the very end, you end up with this crucial equation that eliminates, gets rid of one constant of nature. And that's the epistemological progress of the theory of electrodynamics. And of course, it unifies, in a way, electrodynamics and optics. That's let's say, the key example. And then if you look at several equations in physics, you encounter that. Take this one. I mean, that's just a great insight to relate the force. You can just perceive a force in the static case, and that is related to the kinematics. And of course, Newton had to develop even the concept of acceleration and velocity and so on. But it's a great insight here in that formula. And of course, it's a huge revolution to express local gravity by one single gravitational constant. I mean, otherwise we would have like 90,000 constants of nature for every celestial body in the solar system, and Martians would consider their G and we have our G. So it's a big unification and a big simplification to put all this into this formula. And I should say the visionary idea here is, oh wow, mundane and celestial gravity are of the same nature. Yeah? We should give credit here also to Robert Hooke, who had the idea. But Newton certainly deserves the credit for the formalism, because it's not easy to work that out. And well, just as I said, I want to broaden up a little bit the problem and look at the physics from that perspective. Quantum physics and optics, well, it's a huge insight that you link this, and the story is historically interesting because Einstein contradicted Planck, and Planck was very doubtful about that interpretation. He himself called this H a Hilfsgröße, auxiliary quantity, in German, therefore the H, and didn't believe Einstein and said, oh, Einstein, okay, you're a brave physicist, but you went too far with this hypothesis. No, I mean, it represents the unification of quantum physics and optics, or the link. And then you had another spark of genius, Niels Bohr, on the idea, oh wow, that newly found constant H could be having the physical units of angular momentum. It could be the angular momentum of the electron orbiting the nucleus. Wow. And then that led to the elimination of another constant. In that context, it would be Rydberg's constants, found by Johann Jakob Balmer 30 years before. I left that out, but this is the simplification and the revolution, that you explain Balmer's constant by other constants of nature, beginning with that visionary idea of about the angular momentum. And well, let's come to other problems of physics which are not solved, because people are talking about quantum electrodynamics, but if it would exist, quantum electrodynamics, you would have calculated the number 137. There is no way around. As long as we haven't done this job, you can't seriously talk about quantum electrodynamics, right? And I could add some funny quotes of Dirac here, trashing the concept of renormalization, but we don't have that much time. I think you made also a beautiful video about quantum electrodynamics, right? No? No, so I'm mixing it up. Yeah, because Oliver Consar's, you should do maybe, Oliver Consar's work here is really, really great historical research on that. And well, there are, of course, other essential riddles to be solved. As I said, once you calculate 137, probably you have in your hands a true theory of quantum electrodynamics. On the other hand, if you manage to calculate 1836, the proton-electron mass ratio, by the way, Dirac pondered like 10 years of his life about this fundamental question. You probably would have a unification of atomic and nuclear physics. And let's not forget, Niels Bohr said that presumably we would need another revolution akin to quantum mechanics to understand the atomic nucleus. He was not satisfied in that respect with quantum mechanics. He said there's something big beyond we are still missing here. And well, I just try to remind of these voices. There are a lot of fundamental unsolved problems here. And one I'm like to talk a little bit more, coming back to gravity, is actually why we can say F equals m dynamical acceleration and at the same time local gravity. So y is a equals g, and behind that, of course, is the equivalence principle and the somehow these mysterious properties of mass being subject to inertia and subject to gravity. And I think this is one really serious riddle that needs to be solved. And I talked about this, and it's a little bit a clickbaity title because, to be honest, the problem is not solved yet, but it's as well a wonderful paper by Denis Sciama I featured here. And I think, even if it's not solved technically, I still think he had kind of the key in his hands how to address that in a proper manner. And this is the paper, original paper, Monthly Notices of the Royal Astronomical Society in 1953. And well, he just says that, okay, Newton's theory doesn't address the problem of defining absolute space. He just postulates absolute space, and that's not satisfactory. And I think something is missing here. Did I take an older version? Yeah, it should come your paper, because actually I just mixed it up. It will come later, hopefully. If not, remind me. Anyway, the problem is here. If you haven't heard about Newton's bucket, Newton defined absolute space, saying that, okay, we just put a bucket into rotation, and you see the water is climbing up the wall. So the system, the unaccelerated system, is just the absolute space, and that's it. And then Ernst Mach coming up with a very profound critique, saying that Newton's experiment with the rotating water vessel simply tells us that the relative motion of the water with respect to the sides of the vessel creates no noticeable centrifugal forces, but that such forces are produced by the relative rotation with respect to the Earth and the other celestial objects. No one can say how the experiment would turn out if the walls of the vessel increased in thickness and mass, eventually reaching a thickness of several miles. And that's very, very profound. And you did here a beautiful video also on Mach's principle. And the question is here, well, actually, what would you predict? If you can do the experiment, but what would you predict for the case you stay at rest with your vessel of water and the universe around you rotates? So from a Machian perspective, it's very logical that the water would as well move towards the walls. And the very disconcerting thing is here, we don't have this in our gravitational theories, neither in Newton nor in Einstein's theory. So it's really something, a very deep thing, which is missing. And the most important thing, maybe I think, which is swept under the rug, or you should focus on, this unification of inertia and gravity. And it's kind of sad that it's not considered a problem. You have even a video on YouTube, Einstein talking about inertia, like a little kid. He was told the problem, he wondered about, he was a brilliant mind, he had the means and certainly the intellectual capacity to go deeper into that, but he didn't do it. And I think it's really sad. And well, I think it's a sideline here, but I think this is a matter of scientific culture. Americans, don't be offended. Don't be offended here. It's merely about the history of science. And well, we Germans are well advised not to forget about the history, I guess. And a big part of the book is about the history. And I think you have no chance to understand physics without going to history and see the historical development of the concepts. A little warning here also, someone talking about, oh, this might include the weak force or the wrong force. See the historical development and the evidence and the raw data before you believe this stuff, these concepts, which are not credible if you dig a little bit deeper, apart from the issue of simplicity. That was a sideline. Coming back to the rotation of frames, you can phrase the problem in just another way. You may wonder, oh, why is it that our rest system coincides with what we are observing from the distant quasars, right? That's the same question. Or even in an older famous experiment, why is it that the Foucault's pendulum maintains the true area in which it swings while the Earth is rotating? And yeah, now is your paper, as you beautifully repeated it, Jonathan. Sciama said in his 1953 paper, thus in our theory, we can regard the Earth as stationary and the Foucault pendulum as pulled around by the gravity-magnetic field of the rotating universe. And I think if you manage to do that in a consistent theory, it's just a fantastic result. You know, Leslie, you want to intervene here?
In your view, does this hinge on the idea that like motion is relative, and so there's two equally good perspectives, that the universe is moving or is rotating with respect to the Earth, or that the Earth is rotating with respect to the Earth?
It shouldn't matter. It shouldn't matter from a Machian perspective, which is
no distinction between these two. In your view. Yeah.
Yes, thanks for clarifying. That's my view. It shouldn't matter, and it should be totally Machian, and Sciama's proposal is Machian. That's why we called our Machian gravity meeting in Bonn last year, and Jonathan was giving a very good talk about the Sciama's proposal, and recently he and Dennis dug out even another interesting guy I wasn't aware of, Hans Reissner, who had this very intriguing idea in 1914 about unifying gravity and inertia. That's why I say it's really worth considering history. Much more interesting reading these 100-year-old papers than the contemporary ones. And yeah, there is also other people that have really had interesting thoughts about that. Dennis last year, it's on my YouTube channel, gave a talk on Jürgen Treder, and he also, I mean, nobody reads him, but he also has the same equations, the same ideas here. And yeah, I'd like to mention other people working in that direction. Thank you very much, Manuel, that you try to link it to MOND, but because, I mean, somehow we have to get to these observations also. And I'd like to mention another guy, Markus Schönliner, who is also an engineer working in that direction. Interesting proposals for cosmology based on in that direction. And well, coming back to Mach here, he said, inertia is a consequence of all masses in the universe. And he said, gravity is a consequence of all masses in the universe. And of course, a logical consequence, if gravity is a consequence, you have to be quantitative in physics, you know? And so somehow you have to explain the value of the gravitational constant. This is a consequence of Machian thinking. And not coincidentally, that's precisely what Dennis Sciama in his 1953 paper also did. He gave an explanation of the gravitational constant. And I mean, from an epistemological point of view, that's just what you need to do, okay? You don't want to put up with a number 6.67. Okay, God wrote that number. I mean, hell, think about, you don't want these gods of modernity repeated here without explanation. We want these numbers to be explained. And of course, as Einstein said, I don't like a number that the mood of the creator could have just created in another way. So, and of course, I'm not talking about the number system. So granted, 6.67 depends on the definition of the kilogram. But I mean, the strength of gravity, talk to a surgeon, is a measurable thing. It's a message of nature. We ought to explain why it's not 10 times, why it's not 1/2 of it. It's a riddle. And yeah, if you think about yet from another perspective, if we would manage, I put the factor 4 here for reasons I will explain or not explain better, but it's not that important. Just try to find a formula, but this is huge, you know. I mean, if we would manage to get such a theory that explains the gravitational constant, it would be on the same level as Newton's revolution of explaining the little g, right? So you want to...
It's just if you have time, could you tell us what the reasoning was that led to this intriguing equation?
Also, you have 30 minutes.
I will talk about that.
So how many minutes I have left?
Yeah, it's just if you
I've
have
left.
time.
30 minutes until mandatory Q&A.
Yeah.
Jonathan says he'll explain.
I'll be talking about this.
Yeah. I mean, I can tell just a little personal story. I mean, if you think about just from the units, just always consider the units. You see that very strange meters to the 3rd power divided by second squared kilograms. So somehow you got to suspect that, oh, why couldn't there be a square of some speed in there, speed of light? So you cancel out the meter square second squared. You end up with meters over kilograms. If you think a little bit about the universe, it's just the sum. Another way around doesn't make sense at all. So you put the sum in the denominator here. That's the only. But I come back to this too. The idea, interestingly, many people have had the same idea here. And well, what I wanted to suggest here, that you could see that as a unification of gravity and cosmology, but you could also maybe see it as a unification of gravity and optics, putting the focus rather than on the gravitational constant, putting the focus on C itself and how it might be vary or possibly vary. And yeah, you just would have this nice series of equations continuing in that manner. And yeah, that's the paper we developed. Jan and I developed 10 years ago that thought a little bit more in detail. And yeah, I want to come back suggesting that you should think about variable speed of light in this context, because the starting point of general relativity, you know, was the equivalence principle. And Einstein said, okay, we have this famous rocket here. If it moves in accelerated, you get this curved light here. And at the same time, you must get curved light also if you're just in a gravity field. And the first thought he came up to explain this was, okay, the speed of light is variable. Like you have a refraction. That's banal known optics. And I think Einstein's first idea in that direction was the best one. And as he pointed out already in 1907, but then in 1911 in Prague, from the just proof assertion, where you can read that, it's just let's treat that as conventional optics. We have a medium and we have an index of refraction, and so it comes out that way. So following the history, what's really interesting here, and a little bit of response to your question, is also Erwin Schrödinger in 1925 had the same thought. He speculated about the gravitational potential of the entire universe, which is G sum over MA over RI equals this square of the speed of light, which is Sciama's formula 28 years later, you know? And that's remarkable, but because cosmology didn't almost exist at the time. That was right 1.5 years after Hubble had discovered the first galaxy. Yeah? And already Schrödinger had this bold thought. Yeah. So let's continue the history here. And the problem was, I should say here, why did Einstein give up on that? He made a little mistake considering variable speed of light, yes, but just considered all this variability going into the frequencies. But you have the formula C equals frequency times wavelength. So he thought that all the change of the speed of light would go into the frequency, which is not correct. And later he was corrected. And then after a series of historically interesting, but maybe not that relevant turns of history, he ended up with the geometric interpretation with that four-dimensional picture of space-time, of which he might himself be critical. I remind the quote already about special relativity. When Minkowski proposed the four-dimensional formulation, he said, since mathematicians have taken over the theory of relativity, I don't understand it any longer myself. So, no, but seriously, I think it's one of the worst wrong paths theoretical physics has taken, invoking that, space-time is four-dimensional. Oh, no matter what, okay, three space and one, you just glue it together without thinking about what are we doing, invoking, geez, see the speed of light, it's just a conversion factor. I mean, that's not explanatory power, is it? So if you don't literally depart from your senses, you see that space and time are different quantities, right? Yes. Okay, so you're not just gluing it together. That was another sideline I should make, however, at this point. Let's come back to Schrödinger and the man who eventually fixed Einstein's error, a fantastic scientist, Robert Dicke, known as the discovery of the cosmic microwave background, even if there is another story behind. But he was really a bright theoretician, I would even say in the first place. And he corrected Einstein's mistake and said, no. The change of the speed of light is equally distributed into the wavelength and the frequency. Okay? And that fixes everything. You get out a very nice picture of all the tests of general relativity just with that variable speed of light version of general relativity. And irony of history, and I know it because I wrote an email to Karl Brans, his collaborator, Dicke wasn't aware of Einstein. He didn't know about Einstein. He didn't know that he had made up the same theory, just correcting his error back then. I mean, go figure. It's really, yeah, I come back to that point. So, and yes, there is, of course, a beautiful connection between, to go to that, sorry. Well, hell, the formula is missing here, sorry, but it's the formula of the, oh, it's really sad. It's 1 plus the gravitational,
You have a board.
okay, it's 1 plus the, hope I get it right, yeah, 1 plus the gravitational potential 2Gm over R c squared. And he said, does this, he starts arguing, is this related, this is related to the gravitational potential of the sun, evidently. Is this one related to the remainder of the universe? That is, could we construct a sum over all masses on the universe, whatever factor here, and you get this one from the rest of the universe? That's the bold thought, but as I said, he came up independently from Einstein and everyone else. That was a flash of genius, and it really nicely coincides. Here it is. Just the c squared for matters of a definition, he took it out. But it's the same formula Denis Sciama in 1953 then considered in his doctoral thesis. So, well, that's the second riddle, I think, which is underestimated and you should solve if you have a complete theory of gravity. Please calculate the gravitational constant. We're not believing in gods of modernity. That leads me to another fantastic insight, or let's say, yeah, let's just name the problem before. We don't have an explanation of the Hubble redshift. Okay, so you can argue, some people are arguing there's steady state, but they don't have a really good explanation for the redshift. So the obvious interpretation is, okay, that could be something like a Doppler redshift, the universe is receding. But there is no reason why the hell all this matter should recede from us. So I think Dicke has a spectacular and radical solution for this, saying that, okay, matter is at rest. It doesn't move. It's just light which is spreading. And by spreading light, our horizon is increasing every day. So every day you have the amount of matter that decreases light increased, and that necessarily leads to a cosmological decrease of the speed of light. And I can come back to that later, but that is a first principles explanation of the Hubble redshift. You don't need all this artificial stuff put on top any longer. You know, you want to have it's a consistent theory of gravity and general relativity, and necessarily, if you assume that, as Einstein did, masses cause the speed of light to decrease, you end up with this, with the Hubble redshift. There's no way out. I think this is really something. And if you don't like it, just give me a better explanation of why we have this Hubble redshift, but don't sweep the problem under the rug. So I think, yeah, this is really needed, and I think this also points to a variable speed of light. Third question, last question in between, yeah.
Can you say more on what the cause of this redshift is?
I will. Yeah. Just to complete the series of riddles here, and another very intriguing thing is Dirac's large numbers. How he noticed that the ratio of the electric, and Dirac was also always worried about numbers, 137, 1836, and a huge number you ought to worry about is, of course, the ratio of the electric and gravitational force, which is 10 to the 39. And he observed when the first measurements then came out for the size of the universe, oh, wow, that's approximately the ratio of the size of the universe to the size of the proton. What? Okay, so this is because people are dismissive. Oh, you're playing with numerology. Or this is just coincidence. No, man. You have another coincidence. Also, the number of particles in the universe, defined like this, is the square of that number. How strange is this? Okay. I mean, you meet someone at the other side of the globe accidentally. You know, okay, this is a coincidence, but if you meet another friend at the same time, it's maybe not a coincidence anymore. So what I want to say, it's really strong evidence that there is something behind. And in my opinion, well, I mean, the basic reason why Dirac's large numbers are dismissed because they really would shred to pieces conventional cosmology, because the alternative is so scary to contemplate if you think there is something behind. But I mean, history of science told you that you should pay attention to these coincidences in numerology. I mean, Johann Jakob Balmer did numerology when he figured out that the spectral lines of hydrogen were explained in a simple manner by the 1 over square numbers, right? So let's just do that and, of course, find the theories, but not be dismissive about these coincidences. He said such a coincidence we may presume is due to some deep connection in nature between cosmology and atomic theory. So, yeah, we have this here. And if we would succeed in building a consistent theory, it would be, of course, huge. This is the true unification of gravity and electrodynamics. Maybe the first equation, if you find something. The second equation would be, yeah, you could see as a unification of gravity and cosmology if you find a reason for that. And just to remind you, also Einstein, as a matter of principle, would be in agreement here, because he was the one saying, nature, however, only realizes, he said electrons, but holds also for protons, of a particular size. He said, yes, it does matter how the mass of an elementary particle, no? Because the standard model today would tell you, no, these are just random numbers. No, they are not. You ought to explain things in physics. So just to conclude the circle here, you have Dirac's large numbers. You have, and these include somehow Mach's hypothesis, Mach-Sciama hypothesis on G, but they go beyond. That is, you could realize the Mach-Sciama coincidence with, say, elementary particles that are just 1 million times heavier, and at the same time you have less of them in the universe. So you ought to explain also Dirac's large numbers. And this is a little bit technical, so I'm not sure how much time I have left.
You have 15 minutes until Q&A.
15 minutes, okay. So I just want to invite, because it sounds just so exotic. What? The ratio of electric and gravitational, the size of the universe? Are you crazy? Are you kidding me? If you put things together, I should have started maybe with this one, so I'm going the other direction, but you're all trained in mathematics, so you know what in both directions the equivalence means, so just walk back at the end. So I start with this coincidence, and it's really a strong coincidence. Speed of light, mass of the proton, radius of the proton times p half is equal to the Planck's constant. That holds within the measurement limits of 0.84 femtometers today. So what you can do is say, okay, we multiply by c, you end up here, and then you introduce just the definition of the fine structure constant. Let's assume that some genius is able to calculate that number. So you just put that 137 in here, and you end up with something like the electric force here, and then the rest of the equation is here. But then you, multiply by the electron mass, divide by g, and multiply, most importantly, by the gravitational constant, which is, if you follow the Mach-Sciama hypothesis, something like this. I have replaced the sum here by the mass, so this 4 became 6. You might also argue that's not 6, it's 1.5. Anyway, we're just talking about numbers and orders of magnitude here. But you end up with this one, and then you can cancel a couple of things here. Cancel C, you end up here. So we have something that already suspiciously looked like the gravitational force and the electric force here. So what you do is the electric force and the gravitational force times these cosmological quantities have something to do with the radius of the proton, or eventually you see that very naturally, if you assume this to be true, then you very naturally get the ratio of the electric and the gravitational force by these two quantities. That's 10 to the 80, and these two are 10 to the 40 in the denominator. So you have this factor of 10 to the 40 or 10 to the 39. You would have explained this, okay? I'm not saying anyone has done this. I'm just claiming that this is the way, as a big picture, we need to follow. If we somehow manage to calculate the 137 and 1836, then we would have demonstrated the equivalence. It would make much sense. And I think this is a much more intuitive and insightful formulation of that Dirac's hypothesis. And this is maybe the formula we should work on and try to explain on a very microscopic level. So this is...
So, if I'm not mistaken, this might be exactly the Zitterbewegung radius formula.
Yeah. Because, I mean, then you can go ahead and assume that, okay, let's speculate about if you have a circulating light wave or something like that, and you end up with that. But you agree that maybe this is the intuitive stuff we should try to work in, instead of just wrecking our heads around this crazy coincidence of with the cosmology.
There's a theoretical derivation of this
No.
But that's what...
No.
That was my impression with the...
No. I don't have. I haven't given it a theoretical derivation. That's your job.
There might already be one.
No. I'm just saying that this is equivalent, or more or less equivalent, to Dirac's large numbers, but it's much more intuitive if we want to go beyond. But if you ask contemporary physicists, they would answer, no, it's just coincidence. I mean, the proton is the only stable particle in the universe, and well, yeah, it happens to be in agreement with that, but that's just coincidence. Yeah. Okay, so what I'm saying is, yes?
My work will also touch on the equation on the top left.
Okay, so I can retire soon. Yeah, that's my, and that would be indeed a unification of cosmology and nuclear physics. I think if we go to this formula, some deep connection in nature between cosmology and atomic theory, and well, I made a little provocative video on that. That's in a way Dirac's way to quantum gravity, and anything else is crap. What do I mean by that? That, I mean, if you want to do some unifying stuff on that, please come up with a number. You ought to compute that or give a reason for the 10 to the 39. Otherwise, it's just poetry. Okay? String theory predicted the existence of gravity from the. No. And even if I might like the ideas of Zitterbewegung and Cook 1967 we were discussing, well, be careful. At the very end, we have to come up with this number. So you did already? No.
Well, what I was saying was that I might be wrong about this, but I thought that you could derive that initial formula straight from the Dirac equation.
Well, we should discuss what assumptions go in there. Okay. So, yeah, I don't know why I repeated that. Maybe because it's that important. Yeah, I mean, you should, Dicke was the one providing a true explanation for the cosmological redshift. And yeah, yes, I would want to come back here because you asked me to be a little bit more explicit on that. So I don't know if I get it across. It's not that easy if you if you work with all these changing stuff here. But let's say, okay, first thing is masses influence the speed of light. Okay, curved light passing the sun is deflected because the masses slow the speed of light. All masses in the universe contribute to this decrease. That is, if you assume, but I think that's reasonable, that every day the horizon increases because just light spreads, not because matter is moving, just light spreads. Every day you see more masses, so every day the speed of light has to decrease. You have a cosmological decrease of the speed of light. And of course that affects all atoms here and now, because this decrease of the speed of light would be equally distributed to frequencies and wavelengths. At the same time, it follows from Maxwell's equations that propagating light in an isotropic universe just has to maintain its wavelength. So the wavelength from the distant galaxies cannot change. And so you compare it to the shrinking atoms here and say, oh, there is a redshift. Yeah, that's the reason. So it's by the way, it's completely analogous to the static anisotropic case of conventional optics here, because in this case you just keep the frequency. The frequency in optics is a constant, and all the change goes into the wavelength. In the other homogeneous temporal variation of C case, all the change goes into the frequency in the light wave. So that's the mechanism, more or less, and then, well, you have. Yeah, this is just the same thing. I skip briefly over that propagating light. It's nothing new here, just a little bit more technical. Propagating light maintains its wavelength. And then, yeah, that's a picture. I mean, if you think back then what happened in the first moment, I wouldn't call that the Big Bang because there is no material expansion, you know, but you can imagine, I think there is evidence for a changing universe, evolution of the universe what we see. But if you think back then, what happens if just, yeah, the very moment in which light started to spread, okay? It's interesting that it's not that you have this artificial beginning of time, because at the same time, ironically, yeah, if you say it, at the same time you have an infinite, almost infinite speed of light that translates into other scales of frequency and length scales. So in a way, you're not you don't have this absurdity of the beginning of time, I think. But anyway, it's just, this is where I enter the territory of speculation, clearly, by considering that big flash, light from distant galaxies. And well, if you want to dive deeper here, I'm happy to send you a copy of Einstein's Lost Key, but I mean, you need to get acquainted with this all-changing stuff here. But I fear you have to take my word for it for now. If you consider that timescales are variable, you have the perceived time changing, and you have that number of particles proportional to the square of the perceived time, and that is Dirac's hypothesis. Okay, so such a picture of variable speed of light would be in agreement with that. I think that's really nice. And big flash cosmology, C determined by the mass distribution, expansion rate decrease. I have said that already. Matter is on average at rest as Dicke proposed just light spreads. Apparent expansion due to contracting scales. Universe densely packed with particles. That is the big flash hypothesis. Universe starts at nuclear density. Light starts to spread. I mean, I put a little bit too much into that slide. Okay, it's maybe. So this is speculation. Okay, so maybe you agreed with my critique, or you maybe you agreed with the big problems I outlined, but I don't expect you to agree on the solution, because of course everyone likes his own fancy model, and we disagree with people at the very end. I would agree with you, but then we would both be wrong. And but you can do things in another way, okay? But I'd like to remind you, you have no chance to build a good cosmology without addressing that problem, that unification of gravity and inertia. You have no chance to come up with a good cosmology that leaves the gravitational constant unexplained. You have no chance to build a convincing cosmology without giving a reason for the Hubble redshift from first principles. Forget about any cosmology that doesn't also account for Dirac's large numbers. And I think these are the really huge problems we should focus on. And my guess, or let's say hope, is not very justified, but I think if we arrive there, then maybe things like dark energy and dark matter and the Hubble tension and the nuclear bangs, the lithium problem, things like that, will eventually fade out, okay? But we really should go to these big problems. But I accept if you're our disagreement, and that's why we are here. And I should, to be honest, also give you a reason for disagreement, because I should not hide that there are serious problems. By the way, there are two versions of the speed of light theories, one completely in agreement, but on the other hand, completely agreement with general relativity, but on the other hand, incapable of providing that answers to the gravitational constants. I have made this one. And we're not, unfortunately, able to calculate the perihelion shift. Jan has tried really hard, and he's a smart guy, but we're not here yet, I admit it. And then another problem surfaced, and I tried to work with supernova data. It was a little bit ambitious. Maybe I messed it up. I hope I messed it up, but the result so far is there's a huge disagreement with the data here. So something is wrong here, definitely. But, well, as I said, go to the place Wittgenstein. It might not be clear, but don't lose track of the big problems. And yeah, for me, it's still very intriguing that you can get in such a simple way to a gravitational constant. And it's from another aspect, yeah, I mean, I think I already told about that. Somehow Dirac very well aligns with the idea of Mach's principle here. We should not forget that. And in general, there's another thing about that. In general, we have so many bright minds working in the very same direction. We have historically Ernst Mach, Albert Einstein, Reissner also, thanks to you, worked in the same direction. Schrödinger, Sciama, Dicke, and Dirac. Everyone, I mean, so smart guys. And the thing is, they didn't communicate. They were not talking about their best ideas. And so I think it's a tragedy of science that it went that way, that they didn't have the internet, because it's obvious that there is something in common which addresses these big questions, and it's still swept under the rug by conventional gravity, and for that reason I'm saying it's incomplete. If you want to look up some references, here a paper in Annales de Physique, which essentially contains most of the part of the stuff here. Then there is my book containing fairly almost of this, Einstein's Lost Key. I have a playlist also on variable speed of light, and the general approach about constants and how we should deal with fundamental physics is in my book, The Mathematical Reality. And well, thanks for gathering in Munich. Don't get drunk too much. Thank you very much. Should I or should you?
All right, Q&A time.
So I pick the questions I like. So at that.
Yeah, because people reinforce you.
Who are you?
I would say, we have to relate gravity, in essence, essentially to some kind of quantum phenomenon, meaning every nucleus or some particle must be causing gravity, and the Earth is, of course, just an agglomeration of these particles. So I wonder how that concept of every particle producing a certain amount of change in its space, m cubed over s squared it contains the acceleration of velocity. How does that relate to your idea that like gravitation is related to all the matter in the universe, or somehow the amount of matter in the universe causes or contributes to gravity?
Yeah, that's a good question. And I mean, I myself, I was, say, in love with the ether idea and these defects. And I have also a paper and a playlist on that. But it's unsolved. I mean, the big question here is, what actually is it that oscillates? Who did a video on that? You.
Well, we know it's
But we haven't figured out yet what is the essence. A mechanism. How to represent a particle, maybe an oscillating wave with the same phase, following ideas of de Broglie, but I admit I have no idea that works until now. So, but that made me a little bit skeptical, or maybe ether approaches could be limited, because they usually, ether people wouldn't talk about the entire universe, but I think you have to if you're addressing gravity. Yeah.
Can I give maybe a concrete proposal of a response to that also? Because, I mean, you were asking about linking, the Machian cosmological conception of gravity with a notion of gravity coming from individual particles and so on. And this is just the kind of thing you get in Reissner's model and in these other ones of June and Barber and Cook, where they link. So effectively, the inertial coupling is fitted by Mach's principle. So if you accelerate the entire universe, you want your local frame to also be accelerated, and so you want your particles to also feel that acceleration. But because the particles are vibrating, that produces an additional effect, which then comes out as gravity. So you have a link between like a pure theory of inertia, and then gravity comes out because of vibration and elementary particles. So the inertia links to the cosmos, and then the gravity is a side effect linking to the nature of the matter.
Interesting.
Yeah, it's a very interesting approach. I mean, if we manage to put all this together, it's something big. Okay, no matter. So yeah.
With Dirac's large numbers, we see a bunch of patterns in the numbers. How do we know that those patterns weren't caused by him only taking note of combinations of constants that produced interesting numbers? In other words, how do we know that isn't just produced by selection bias?
No. It's well, I mean, to be fair,
coincidence. There's not enough to work with.
You want me to answer? Or, okay. To be fair, these numbers are orders of magnitude. As everything you measure is cosmology is as dirty as one order of magnitude, if you're honest, you know. So you know that I switched a little bit between 10 to the 40 and 10 to the 39, but there might be good explanations. I mean, you put just the fine structure constant in here, which is also maybe reasonable. So, but it's not selection. I mean, Dirac really thought about a whole lot of time how to produce numbers in general in physics, you know? And then you have evidently 137, 1836, but there is nothing like a couple of thousand in between. You just don't get that. The only possibilities where you can get out pure numbers from constants of nature is that one, you know? There's no 10 to the 20 or 10 to the 60 or something like that, no. So there is something. Yeah, I should mention that some people would come up with Planck's units here. They're just, a poorly understood version of Dirac's large numbers taking the square root of 10 to the 40. But there's nothing essentially new here. Yeah, but it's not a selection bias. It's really just these numbers, and we need to worry about. Yeah.
There's also an important difference between like selection bias in experiments in biology or something versus like when you're talking about quantities in physics that are meant to be completely universal. So they're not arbitrary measurements. I mean, we've seen the pattern. These are numbers that are, you know, the same for every person wherever you are in the universe, that are meant to be, you know, universal constants. And so you don't have an infinite amount of these numbers to work with. Right? You can't just generate more of these universal constants.
The patterns are in ratios of the numbers and multiplicities of the numbers.
Yeah.
So
Yeah. Just play around with the usual constants of nature. One very interesting thing is here, for example, if you leave out the gravitational constant and you take all the rest of the constants of nature, you're unable to produce a mass or an energy. Think about that. So there is no way just for a genius to say, oh, I combine the electric field and maybe I find an approximation to avoid the infinities and so on, and I come up with the mass of the electron. You're not going to do that. I give you $1,000 if you do that. It's impossible. But you need the gravitational constant. Without the gravitational constant, you never arrive there. You know. But I think it's the key to fundamental physics to wonder about these constants of nature, units, and how to calculate this. Oh, sorry.
So you need to introduce another fundamental constant with dimensions of mass in the standard model to get the rest of the masses.
Of course,
That's the trick they do. There are just four fundamental dimensional constants, and one of them is something related to the hits in order to get the masses, and that's a mass or an energy.
Mm-hmm. Yeah, but nobody has ever calculated a mass in the standard model, right? So you can
do it by dimensional analysis.
They're all post hoc calculations, like the one string guy said, oh, I have a calculation here that predicted the Higgs mass. Yes, he had all 300 other calculations in all ranges of this. Okay, please.
I only hope that my numerology fine structure constant calculations revealed to be basic some topological and geometrical basis next year when I will publish my part 3 of my theory.
Mm-hmm. I wholeheartedly agree with you with the goal. That's really, but of course, we're also skeptics, and you have to produce a couple of digits, to be convincing. It's not easy, but anyway, Mm-hmm.
Can we go back to the slide with the equations? Where we have
someone who wants the equations. Which ones? Oh, which?
the one where there was just equations.
Just the equations. That was. I think it was how to derive. I see. Okay. I think this.
Yeah, these ones, yeah.
Mhm.
So, wait, are you working from this first one at the top left? To
I-
calculate?
Yes, I'll work this way, and then I jump up here until here. Yeah.
So, what are the additional assumptions that go into?
Yeah. Okay. The assumption is here. Well, in a way, you can say you need to assume that this is calculable as a matter of principle. If you want to have a good final theory of everything, you should also be able to calculate 137. If not, you just end up with orders of magnitude. And at the same time, you should be able to calculate the electron-proton mass ratio. Otherwise, you end up with orders of magnitude. And the third assumption is, of course, that you put in also this one. Yeah? But it's woven into this argument here by if you replace the gravitational constant here by this term. But I can cancel the 6 and write 1.5 if this is your problem. I do it for you. Yeah.
There's one good question. How do we...
Yeah, but did it finish? Did that answer your question, or?
Well, so because you started out by saying that this equation at the top is a coincidence that is not explained. Is that right?
Yes.
Because I was commenting that it looks to me like that's just the definition of the Zitterbewegung radius of the proton.
But the radius of the proton is an actually measured value.
Right. The same also applies to Planck's constant. And how is it measured?
Yeah, I mean, Jonathan, if you come up with a theory that perfectly makes a formulation with this result, and you go to nature, and that's fine. I mean, that's really something big. But I would say it's not accepted yet.
Okay.
I'm just pointing out this is a much more intuitive and much more promising version to work on, as you seem to indicate, than this weirdly looking coincidence of forces and the universe, because people sometimes are dismissive for that very reason, are dismissive about this.
Okay, well, I'd like to look at this all in detail.
One question is, how do we know the mass of the universe? How do we know the number of particles in the universe? Couldn't it be much more extended than, the visible?
Well, of course. I mean, as a matter of principle, you can say the universe is finite, but if you believe in you don't have to believe in the Big Bang, but as I said, I think it makes sense to assume that the universe is evolving, that you have a light cone that spreads. So every day you have your horizon increasing, and it's a well-defined quantity how much mass is inside your horizon. In the visible horizon. By the way, I should mention the guy I mentioned before, Schönliner, who developed another version of how to consider an infinite universe with an exponential weighting that ends up with a finite mass, but that's a sideline. But it's a well-defined quantity, but as I said, everything is dirty in cosmology. Forget about precision measurements here. We have always orders of magnitude, and that's how it is. Yeah? But we're talking of orders of magnitude. Nonetheless, these are remarkable coincidences.
Can I also add to that? There's also, a lot of this kind of reasoning, I think, hinges on an identification of the observable universe with that which is in causal contact with you, and that only that which is in causal contact with you should even be considered to be physically real from your perspective.
Yeah, that's a good way to phrase it also, yeah. Mm.
Any further questions? All right, I'll take you. Thank you.
Yes.